Hi, in the previous session we have covered what aromaticity is, we have covered the Huckel's rule, we have discussed every criteria in detail that must be possessed by the molecule in order to be designated as aromatic. And in this session we are going to cover the examples which we have to find whether this molecule is aromatic, anti-aromatic or non-aromatic. So let us see one by one. We are going to cover the first case in which there are going to be 2 pi electrons in the system. I want you to recall these two series of numbers that the aromatic molecules can have electrons count of 2, 6, 10, 14 and 18. This was series for aromatic molecules. On the other hand, there was another series of 4, 8, 12 and 16, and this is for anti-aromatic molecules. So we are covering this particular number, that if any of the compound possess 2 pi electrons, then how that molecule can be aromatic. So we are going to cover 2 examples inside it, and both of these examples are of ions. These are not molecules, these are charged species. That is why these are called ions. So first example is of a molecule which is Cyclopropanil Cation. Let me make you understand what cyclopropanil actually means. For this we have to go to this place. Cyclopropene. Let us first say what is cyclopropane. So cyclo means cyclic and propane means there are going to be 3 carbons. So this is the structure of cyclopropane. If I put a double bond inside it, then this molecule becomes cyclopropene. Ene means there is double bond. Now whether this molecule is aromatic or no? The answer is no, because this carbon is not the part of the conjugation. You can see there is no charge here, there is no p orbital here. So this molecule is not aromatic, because there is a carbon gap. This carbon does not possess any p orbital. Let us take this structure as the example. Here there is one double bond in the cyclopropene and there is positive charge on this carbon. Now whenever there is a positive charge, it means there is empty p orbital. We have seen p orbitals in the case of double bonds. So this means that the p orbitals have 1 electron each. That is why there is 1 pi bond inside the molecule. When there is a positive charge on any carbon, that means there is 1 p orbital and the p orbital is empty. There is no electron inside it. So this is the case in this molecule, which is cyclopropanil cation. So is there conjugation in all the atoms of the molecule? The answer is yes. There are 2 p orbitals here, there is 1 p orbital here on this carbon also. So there is conjugation, the molecule is planar, the p orbitals are perpendicular to the ring, and if you do the count of the electrons, the answer comes out to be 2. Because there are 2 electrons in these orbitals, there are no electrons in this particular orbital, so the electron count is 2. It is following the number series of aromatic molecule which we have studied in the past. Let me rewrite this series again here for you. The count of 2, 6, 10, 14 and so on follows aromatic molecule series, and count of 4, 8, 12 and so on would be considered as anti-aromatic molecules. We will see what anti-aromatic molecules are, but we will simply do electron count here and try to understand whether the molecule is aromatic or anti-aromatic. So this molecule is aromatic. Okay, this is non-aromatic because it is missing out one of the criteria. So one of the criteria is missed, the molecule is simply non-aromatic. In this case, the molecule is planar. It has conjugation on every carbon because there is negative charge over here. Anion means negative charge. So there is 1 p orbital on this carbon and the total number of electrons which are present in this p orbital is 2. So there is 1 electron on this carbon with a p orbital, there is 1 electron in this p orbital of this carbon, and there is 1 more p orbital on this carbon which has 2 electrons. So the molecule is planar. It has perpendicular p orbitals. There is conjugation on every carbon, but if you do the electron count, the answer comes out to be 4. So this molecule is actually anti-aromatic. Okay, this was non-aromatic, this is aromatic, and this is anti-aromatic. Let us take the more examples. Here we are missing any conjugation on this carbon. So this molecule is also non-aromatic. This is Cycloheptatrine Cation. This means there is a 7-membered ring and there are 3 double bonds because triene and cation means positive charge. So there is going to be a p orbital on this carbon and there is going to be no electron inside this p orbital. So if you do the electron count, there are 2 electrons here, 2 here, 2 here, and there is none over here, but there is conjugation. So the electron count is 6, and if you see the series, then it follows the aromatic criteria. So this molecule is considered as aromatic molecule. On the other hand, if you see this example, there is cycloheptatrine anion. Anion means there is negative charge over here. So there are 2 electrons here, 2 over here, 2 over here, and 2 over here. So if you do the electron count, the answer comes out to be 8. So this follows the anti-aromatic criteria. So this molecule is also anti-aromatic. So these 2 molecules are anti-aromatic, these 2 are aromatic, and these 2 are non-aromatic. I hope you are able to figure out how to designate the molecule as aromatic, non-aromatic, and anti-aromatic. So this way, these molecules would be considered as aromatic. This is nothing but a cyclopropanil cation. The phenyl group doesn't matter. We have to see this ring itself. So there is one positive charge which is delocalized. That is why it is written in the center. And it is saying that it is cyclopropanil. That means there is one double bond also in the ring. The same goes for this molecule also. It is butadiene. So this means there are going to be 2 double bonds inside the ring. And there is also 2 p electrons, 2 p orbitals which are empty. So it's a di-positive cation. So this means there are 2 electrons here, 2 electrons here, and there are 2 positive charge. This is the example of anti-aromatic molecule because the electron count is 4. So it is the example of anti-aromatic molecule. Okay. Let us move to the second subcase, which is possessing 6 pi electrons. The very good example of this case can be our benzene ring. Benzene has 6 pi electrons, so it is example of 6 pi electron system. So benzene is very good example. Let us see these examples in detail. The first molecule is Cyclopentadienyl Cation. Cyclopenta means 5-membered ring which is cyclic, and there is going to be 2 double bonds, and it is anion. Anion means negative charge. So 2 electrons over here, 2 electrons over here, and there are 2 electrons in the p orbital which is present here. So the total count is 6. So this way this molecule is also aromatic. We have covered this example also, cycloheptatrine cation. So this molecule also has 6 electrons. So that is why this molecule is also aromatic. We have to cover one more subcase which is of heterocyclic molecules. The term heterocyclic is derived out of the existence that there is a cyclic molecule and there are heteroatoms inside it. Heteroatom means any atom apart from carbon is considered as heteroatom. So you can see there is oxygen over here, there is sulfur over here, there is nitrogen, and there is again a nitrogen. So all these molecules are heteroaromatic molecules. Heterocyclic or heteroaromatic, these are the 2 terms which can be used synonymously for these molecules. So let us see how these molecules are aromatic. We will consider each example in detail. So let us first take the example of furon. Furon is nothing but a 5-membered ring with 1 oxygen inside it. So here you can see that there are 2 double bonds inside this ring. So that means there are 4 pi electrons and there is oxygen as the heteroatom. So oxygen possesses 2 lone pair of electrons. So this means one of the lone pair is in this direction and one lone pair in this direction. So this particular lone pair is to be in the same plane of the ring. As you have previously seen that, so I must recall you that oxygen is an atom which contains two lone pair electrons. So there are two lone pair orbitals. One is going to be in the same plane of the ring and the other is going to be perpendicular to the ring. So as we have seen in the Huckel's criteria, that the electrons or the orbitals should be perpendicular to the ring itself. Recall the criteria number 2. So in this case, what is going to happen is this lone pair won't be participating in delocalization, only this lone pair would be participating. So you do the electron count, the answer will come out to be 6. So this way this molecule is also aromatic. Let us take the example of pyridine. Pyridine is nothing but a 6-membered ring with one nitrogen. So here the nitrogen is sp2 hybridized. Let us study the hybridization of pyridine. Before this, I want to make you understand is that the lone pair of this nitrogen is not going to participate in delocalization because it is going to be in the same plane as of the ring. It is not perpendicular. So how to figure out which lone pair orbital is perpendicular to the plane and which is not? So for this we have to understand the hybridization. So nitrogen, just like carbon, have 3 hybridizations. One is sp hybridization, the other is sp2 hybridization, and the third one is sp3 hybridization. So nitrogen which is attached to any other atom with one double bond would be called to be in sp2 hybridization, because the other leftover p orbital would be participating in making the double bond. And nitrogen which is not the part of any double bond would be having sp3 hybridization. So Pyrol has sp3 hybridized nitrogen. And example of sp hybridized nitrogen can be your cyno group. So in this case the nitrogen is the part of a triple bond. So the 2 p orbitals are being used to form 2 pi bonds and one sp orbital is being used to form sigma bond. Let us not go much in detail about it. So I hope you can find that pyridine has sp2 hybridized nitrogen. So the p orbital of the nitrogen would be perpendicular to the ring. So lone pair would be in the plane of the ring. So if you do the electron count, the answer comes out to be 6. So this way pyridine would be considered as aromatic. Let us take the example of Pyrol now. Pyrol has sp3 hybridized nitrogen, so there is no p orbital with nitrogen. So that means the lone pair orbital would be perpendicular to the ring itself, and lone pair is now going to participate in delocalization. So if you do the electron count, there are 2 electrons over here, 2 over here, and 2 are the lone pairs. So the total electron count becomes 6. So this way your Pyrol molecule is also aromatic. This way we have finished the heterocyclic molecules. If you talk about the thiophene, then sulfur also possesses 2 lone pairs. Just like the furon, there is going to be one lone pair which is in the same plane of the ring, and one lone pair would be in the perpendicular to the ring. So only one lone pair will participate in delocalization. So the total electron count would be 6. So this way your thiophene would also be considered aromatic. Let us take the third and the final subcase, which is of polycyclic compounds. Polycyclic means there are going to be multiple cyclic elements in the structure. So if you take the structure of naphthalene, you can see there is one benzene ring fused with the other part which also appears like benzene. So the total count of pi bonds inside it comes out to be 5. So 5 pi bonds have 10 electrons. So if you compare it with the electron series, then this molecule is also aromatic, because having 2, 6, 10, 14 molecules is considered as aromatic. So 10 electron count naphthalene. If you count the number of pi electrons in this case, then the count would be 14. So anthracene is, because it has 14 electrons, it is also aromatic. The same 14 goes with the phenanthrene. There is only shift in the placement of the third ring. So this molecule is phenanthrene, and this molecule is also aromatic. So this way we have covered that what are the examples of aromatic molecules. We have covered the different classification of these molecules, and such examples are asked in competitive exams. So this is why this topic was very important. So that's it for this session. In the next session, we are going to cover a leftover topic which is related to anti-aromatic molecules, because your syllabus does not ask you to study anti-aromatic molecules, but sometimes the questions are asked. So there is a leftover topic which we will cover in the next session, and that would be based on anti-aromatic molecules. So see you in the next session.